Good evening. Welcome to the live interaction session for our week 9 of our course Computational Fluid Dynamics. Basically, in week 9, we are more concerned about the solving methods for our linear algebraic equations. So, when in CFD, what just recapping the whole process. In CFD, what we will do is we will be uh, uh, the governing equations in CFD. When we have a problem in our hand, uh, to do the CFD methodology, what we would be following is to apply the governing equations that will be uh, matching to the physics of the problem. Then this governing equation will be reduced to uh, a set of uh, algebraic equation. So this algebraic equation has to be solved. When this algebraic equation, when we have a domain, uh, suppose we are having a computational domain of a rectangular mesh. So in each node of the cell, each node of this domain, this algebraic equation has to be solved. So for that, it will make a system of algebraic equation which can be uh, uh, written as in matrix form as Ax is equal to B, where A is the coefficient matrix and X is the unknowns. So to solve this matrix or this system of algebraic equation, we need some methods. So some basic methods that we will be using for our uh, solving the system of equations that will be resulting from the discretization of our domain uh, is discussed here. So how we can uh, solve these algebraic equations, or what are the methods we will be following. So some of the basic methods are discussed in this section or also in the week 9 videos. So moving on to questions. First question, which statement is false about Gauss elimination? So Gauss elimination is one of the method or one of the basic methods that can be used for solving. So Gauss elimination is a method for solving system of linear equations. So the question is about which is false about Gauss elimination. Options are: it can be computationally expensive for large systems. Option B, it is a direct method for solving linear systems. Option C, it's not suitable for sparse matrices. Option D, it involves row operations for elimination. You can try to answer the question. So if we can check the options one by one. Uh, in Gauss elimination, what's being done is we will be doing raw operations to eliminate some of the elements to so that it becomes easy to solve for the unknowns. So basically, when Gauss elimination is based on raw operations, it will become computationally expensive for large systems. So this is a this is true. This option A is true for uh, Gauss elimination. Second one, it's a direct method for solving linear systems. Again, it's a direct. It is a true statement. It is a direct method for solving linear systems. Option C, it is not suitable for sparse matrices. So, what are sparse matrices? Sparse matrices is some matrices where uh, the number of zeros or zero elements in the matrices will be greater than number of non-zero elements. So, or comparatively, there will be a number of zeros will be higher. Uh, it will be greater or almost equal to the number of non-zero elements. So, the statement is not suitable for sparse matrices. Uh, there is a notion that uh, uh, sparse matrices cannot be solved by Gauss elimination. The only issue is when we have a pivot element becoming zero. So sparse matrices can be solved with Gauss elimination, but only issue is when there is a pivot element. That is when a diagonal element becomes zero. So that can be uh, uh, avoided by reordering the rows actually. So the thing is, sparse matrices can be solved with Gauss elimination. So this statement option C is false. So this is our answer. So again, I told you the first statement in the start itself. It is Gauss elimination is uh, uh, by Gauss elimination is basically carried out by doing raw operations in the matrix. So this is true. So only statement which is false is option C. So that's our answer. Moving on to next question. Which of the following statements is not true about TDMA method? So TDMA method is called is tri diagonal matrix algorithm. So again the question is to find a false statement about TDMA method. So options are option A, it is highly efficient for solving tridiagonal systems. Option B, it is an iterative method that requires an initial guess and repeated calculations. Option C, it is particularly useful in CFD for solving discretized governing equations. Option D, it can be applied line by line in multi-dimensional problems. I can try to answer the question. So here, some of the options can be easily eliminated. For example, the first one, it's a highly efficient for solving tridiagonal systems. It is efficient system, and again from the name itself, it is for tridiagonal system. So this is a true statement. It's a true statement. Uh, Again, it is option C. It is particularly useful in CFD for solving discretized governing equations. So if it was not useful in CFD, we won't be studying that. So again, it's a true statement. Option D. It can be applied line by line in multi-dimensional problems. So that's again how it is done. It's a line by line procedure. So this again, the fourth option is again true. So only uh, option left is it's an iterative method that requires initial guess and repeated calculation. So there is no guesswork in TDMA. So option B is false. So our answer is option B, which is not true. Again, another question on TDMA method. What type of metric structure does the TDMA method works best with? Options are full matrix, sparse matrix, banded matrix, and diagonal matrix. You can try to answer the question. It's very easy comparing to the while doing the two questions. First two questions, it is much easier compared to that. Try to answer the question. Okay, again, if you remember, uh, this TDMA is tri-diagonal matrix. So from that name itself, we can uh, imagine a matrix where this is the main diagonal, this is the subdiagonals, these two are the subdiagonals. So when a matrix has elements like these, so that is there is elements in the main diagonal, also the diagonals just above and below. So such a matrix is known as tri-diagonal matrix. So we can try to find which will match this one. So from these options, option C, banded matrix. That's you can see this kind of three bands. So the option C, that's is a banded matrix. That thing works well with the works well with this tri-diagonal matrix description. So option C is the answer. Again, if you see option B can also be chosen as an answer because apart if there is only three diagonals, only there is only elements on three diagonals. And then again, uh, it can be a sparse matrix. So sparse matrix says that number of zeros should be more than number of non-zero elements. Uh, Also, in these subdiagonals, some elements can be zeros. So it can also be a sparse matrix. So for both sparse matrix and banded matrix, the TDMA method can be used. Even though the TDMA method excels in solving tri-diagonal matrix, the tri-diagonal matrix can be uh, uh, tri-diagonal matrix or such matrices are termed as banded matrix because there is only elements in a band or a belt. So it is such matrices are known as banded matrices, and also depending on the number of rows and columns, it can be sparse matrix. Moving on to next question. In a finite volume discretization, the advection equation of CFD, which of the following variables would typically result in a tridiagonal coefficient matrix? So when we are discretizing the terms, we know we have the momentum equation, um, current equation, all such equations. So typically when we are discretizing the equations or part of the uh, domains, which of the variables are most likely to form a tridiagonal matrix? So the question is, options are uh, option A density, option B velocity, option C pressure, or option D all of the above can result in tridiagonal matrix. You can try to answer the question. And please keep in mind that it is particular, the question is particular about advection equation. Yes, the answer is option B, velocity. Mostly the velocity term in the advection equation is the one that leads to tridiagonal coefficient matrix formation when we are using finite volume methods. Moving on to next question. When applying TDMA method in a CFD code, how are the boundary conditions BCs incorporated? Options are, they are directly included in the tridiagonal matrix coefficients. Option B, they are treated as separate condition after solving the system. Option C, they are not relevant for TDMA algorithm. Option D, they require modifying the TDMA algorithm itself. So question is about the treatment of boundary condition while using TDMA method. You can try to answer the question. You can inbox your answers. Yes, the answer is option is A. Right. They are directly included in the tridiagonal matrix coefficients. So if we know how discretization is being done, so when we have a domain, suppose we have a, so the boundary conditions are the conditions are prevailing in the boundaries. So it will depend on how the boundary conditions, our our discretized equation, when we are discretizing the nodes near the boundaries, the dots near the boundaries are discretized taking the or considering the boundary conditions. So this should be embedded in the discretization itself. So this I already told you the discretized equations are discretized equation or the linear equations is what uh, uh, from which what we are getting the coefficient matrix. So the linearized equation, the boundary conditions are embedded in the linearized equation, which is then converted into matrix form from which the coefficient matrix is generated. So that is our option A becomes true. We don't have to do any special treatment for embedding tridiagonal matrix, embedding boundary conditions in while we are using TDMA method. Moving on to next question. Compared to other methods like Gauss elimination, what is the potential advantage of TDMA in CFD applications? So it's a comparison question between Gauss elimination and TDMA method. Options are: option A, it handles full matrices more efficiently. Option B, it is more memory intensive. Option C, it is specifically designed for tridiagonal systems leading to computational efficiency. Option D, it requires user intervention. It requires less user intervention. So, when compared to Gauss elimination, what is the main advantage of TDMA method? Try to answer the question. So, if we have learned what is TDMA method and its algorithm, it basically works with forward substitution, forward elimination plus backward substitution. So, if we can boil down the entire TDMA method into two parts, it is forward substitution and forward elimination and backward substitution. So that is, we will be reducing the uh, by moving forward in the raw numbers, we will be eliminating uh, elements, so that we can work with less data. And while backward substitution, we will be plugging on the previous values of solved variables back in the system to find out the or to solve the remaining unknowns. So that's the general method followed in TDMA method. So uh, if you see the options, it can see we can see that the first option is it handled full matrices more efficiently. Now, when there are the matrices is full, the forward elimination process will take uh, it will take more time, or it becomes more computationally expensive. So this is wrong. It is more memory intensive. So when is something more memory intensive, when we have to store some values, then only the terms become memory intensive. So when we are eliminating things, actually what we are doing is to uh, reduce the memory usage. So that's again a wrong statement. And third statement, it is specifically designed for tridiagonal systems. That is true, and which will lead to a computational efficiency. Our answer is option C. And option D, it is kind of an ambiguous statement. It says it requires less user intervention. Actually, it will depend on the problem. So from this set of options, option C is the best. Next question. Which of the following properties of a CFD problem might make TDMA less suitable as a solution method? So the question is about potential drawback or potential limitation of TDMA method. Options are: option A, linearity of the governing equations; option B, steady state nature of the flow; option C, complex geometry with irregular boundaries; option D, high Reynolds number flows. Again, a simple question. Try to answer the question. You can inbox your answers. So, yes, yeah, we are coming to that. Let's see about the options. Uh, First option is the linearity of the governing equation. So, TDMA method is uh, used for solving system of linear equations. So, it is not a limitation or drawback or something. And again, steady state nature of the flow. No, again, it's not a limitation, because TDMA is kind of best works with uh, steady state problems, that is parabolic problems. Suppose if you see del square t, that is steady state. This is a Laplace equation for temperature, and such kind of equation also, if you reduce, it can boil down to tridiagonal or pentadiagonal systems. So the TDMA method can be easily used in steady state problems. And again, next, of course, option D is high Reynolds number flow, that is turbulent flows or uh, high speed flows, or turbulent flows, we can say. So actually, TDMA can be utilized in turbulent flows or higher Reynolds number flows if the turbulence is modeled properly modeled. So the one other difficulty in CFD is that complex geometry with irregular boundaries. So C is our answer. So we have already said that while discretizing itself, the boundary values gets embedded in the linearized equations. But when it comes with complex geometry with irregular boundaries, it won't be directly resulting in any uh, tridiagonal matrix or something. We have to make it tridiagonal matrix. So that is another added computational difficulty when complex geometry with irregular boundaries are being solved with TDMA method. Moving on to next question. How can the TDMA method be used in conjunction with other numerical techniques? So the question is about how TDMA works well with other numerical techniques in a CFD simulation. Options are: it can be used for pre-processing step to prepare the system for a more complex solver. Option B, it can be employed for specific parts of the domain with tridiagonal structure. Option C, it cannot be combined with other methods effectively. Option D, it is the primary solver for most CFD problems. Try to answer the question. You can inbox your answers. So the answer to this question mostly lies in the option itself. Mm, like this kind of a or thing, what will happen when we are using TDMA with other numerical methods? So first option is it is a pre-processor step. No, it's not a pre-processor step. It's kind of a detailed solver processing itself. So option A is not suitable for our concerned problem and concerned question. Next one, it can be employed for specific parts of the domain with tridiagonal structure. Suppose we are uh, having a multi parts, I mean, our computational domain or geometry is larger, and it have specific parts with different boundary condition and all. And in such a scenario, uh, our tridiagonal structure can be used for that particular part. So that's a statement which that is true. That is right. So our answer is option B. So option C is it cannot be combined. It's wrong. It can be combined, and it is not the primary solver. So our options that works well for the question is option B, that it can be employed for specific parts of the domain with tridiagonal structure. So such approach is called hybrid approach when we are using different solvers for different computational domain. So we can choose particular solvers for particular computational domains, uh, keeping computational efficiency in our mind. Next question. What is the computational complexity or the order of operation of the TDMA method for solving a tridiagonal system of size n? So when we have a n-sized system, n-sized matrix, then what will be the order of operations? Options are option A, order of n cube, option B, order of n square, option C, option order of n log n, option D, order of n. So slightly a mathematical side of the problem. Uh, so still you can try to answer the question. When we are using TDMA, what is the computational complexity associated with the method? You can inbox your answers. No, it's not option B. It's actually option C, order of n log n. Computational complexity of TDMA is in n log n. Moving on to next question. The next question is on stream function vorticity method. The question is, how does stream function vorticity method handle viscous effects in the incompressible flows? Actually, this part of the questions are mostly linked with, mostly covered in week 8 of the lectures. Still, we can try to answer the question. The question is on how does the stream function vorticity method handle viscous effect in incompressible flows? Option A, it directly incorporates viscosity terms into the governing equations. Option B, viscous effects are neglected, making it suitable only for inviscid flows. Option C, Viscous terms are included through additional source terms in vorticity equation. Option D, this method is not applicable to viscous force, not applicable to viscous flows due to limitations in vorticity formulation. You can try to answer the question. You can inbox your answers. No, it's not option D. Let's see what stream function vorticity method. So, if you remember from basic fluid mechanics, stream function is psi and vorticity that we represent by omega. So, in stream function vorticity method, what we do is we will be uh, using stream function and vorticity to model our governing equations. That is, considering a two-dimensional flow field, our velocity u velocity and v velocity, that is velocity in x direction and y direction, is converted into psi and the stream function and vorticity through the existing relation between stream function and our velocity components, and the equations are solved for uh, stream function and vorticity. So the issue is viscosity is, we know the viscosity is, which is the relation between shear stress and shear rate, is mostly associated with u and v. So such terms it will be difficult to include or relate with stream function and vorticity. So what we need is we have to uh, add some additional source terms. So what we can't include in the general variables, we have to introduce those variables or those effects through additional source terms or source terms. So there will be some source terms plus which all things we can't model, that also will be modeled as source terms. So option C is our answer. Moving on to next question. A limitation of stream function vorticity method for boundary condition involves. So the question is on the limitation of stream function vorticity method while sorry the question is on the limitation of stream function vorticity method while incorporating the boundary conditions that is existing. Options are, the question is the limitation of stream function vorticity method for boundary condition involves. Options are specifying both stream function and vorticity at all boundaries. Option B, difficulty in implementing no-slip boundary condition on solid walls. Option C, inability to handle flows with free surfaces. Option D, all of the above. If we can think a little, then this question is easily solvable from my explanation for the previous question. Try to answer the question. You can inbox your answers. Yes, option C is true. But let's see what this is really means. So I already told you the stream function is psi and vorticity is omega. Where if you remember, the stream function psi is something uh, which should follow the Laplacian equation. So the stream function is chosen in such a way that uh, dou psi by dou y is equal to u, and dou psi by dou x is equal to minus v. So this is the relation existing between stream function and the velocity components. So uh, in our problem, or in whichever problem we have, the boundary conditions will be mostly in velocity. If it is a digital boundary condition, it can be either values of velocities, pressure, or something like that, or the conditions like some Newman conditions. So here, so the major difficulty is that when we are solving for psi instead of u and v, we have to convert all the boundary condition in terms of psi, not u and v, or pressure, or whatever there it is. So all the boundary condition, all the existing boundary conditions should be modeled or converted in terms of stream function and vorticity. So option A is also true. And again, difficulty in implementing no slip conditions on solid walls. We know that while the flow is near some solid wall, the adjacent layer, the most nearest neighbor, nearest layer of fluid to a solid wall, is considered to be in rest, or there is no movement in between those two. So such a condition is called no slip condition. So that no slip condition cannot be applied for, that's in terms of v. So that will be difficult in implementing with the vorticity. Again, inability to handle free surfaces. So this is a solid wall, this is a solid surface, where the third one is inability to handle the flow with free surfaces. That is when we have a flow, fluid flow or open channel flow, the water or liquid or fluid, whichever will be having, is have an open boundary. So it will be it won't be having any restrictions or any solid boundaries there. So such surface are called free surface. So in free surface, like no slip condition, we will be taking no shear condition or zero shear condition. That is dou u by dou y. This kind of condition will be zero. So free surface are designed with no shear. So all the three become valid when we are using stream function vorticity method. So our right answer is option D, all of the above. That is, stream function vorticity method can struggle with imposing all necessary boundary conditions, including no slip, complex geometry flows, uh, free surface flows, everything, all the thing, because everything we have to uh, remodel in terms of uh, psi and omega. Next question. Which method for solving linear system of equation in CFD involves forward and backward substitution steps? So the question is about finding a method from the given options which uses both forward and backward substitution. Options are option A, Gauss elimination, option B, Jacobi method, option C, LU decomposition, option D, relaxation method. can try to answer the question. You can post your answers. Yes, you are right. Answer is option C, LU decomposition method. So in LU decomposition method, I already told you we will be writing the coefficient system of linear equation as Ax is equal to B, where A is the coefficient matrix. So this coefficient matrix is written as A into A is equal to L into U. So where L is the lower triangular matrix and U is the upper triangle matrix. So there is two set of matrices which so in this we have to do the forward as well as the backward substitution, or which allows uh, forward or backward substitutions. So option C, LU decomposition is the answer. Moving on to next question. This next question is on Jacobi's method. Jacobi method. The question is, in Jacobi method, the update equation for the variable involves its current value and the value of its neighbors from dash iteration. Options are previous iteration, option B current iteration, option C next iteration, option D average of all. Try to answer the question. You can inbox your answers. No, it's not the uh, current step. Option B is not the answer. Okay, let's see what is an update equation uh, uh, and what is Jacobi's method. So uh, let us consider I will explain with the example. So let's take uh, the same one, steady state heat transfer equation, that is Laplace in for t del square t is equal to 0. So let us consider a rectangular domain. I'm just taking only 4 nodes. Let this node is I comma j. This one is I minus 1 comma j, and it is I plus 1 comma j, and this one is I comma j plus 1, and the one below is I comma j minus 1. So these are the 4 ends of a cross. So when we discretize this one for temperature, the equation with the central difference scheme, I am using central differencing scheme in x and y direction. Let's take delta y and delta x as the distance between nodes. So the equation will become something like t of I comma j is equal to t of I plus 1 comma j plus t of I minus 1 comma j plus t of I comma j plus 1 plus t of I comma j minus 1. Okay. The whole divided by 4 given we are considering delta x is equal to delta y. We can try to discretize the equation. We have done it in second week and all. So when taking delta x is equal to delta y, the terms of delta x and delta y will cancel out. Then our equation becomes something like this. So Tij value can be found out as the average of its 4 neighboring points. So the update equation is something uh, when we are at nth step, then the update equation is the equation or which the values that will be using at n plus 1th step. So that's an update equation. So when we are at n plus 1th step, which values we will be taking? So which of the values from n plus 1, that current step itself, or the previous step n, or again the next step, that is n plus 2, which all the values will be taking. So this value, this left hand side, will be of n plus 1. That is, to find out the current value of Tij, what we will be needing is the values. If we are taking the current values of the cells, then the entire subscript will be n plus 1. If we are taking all are from the previous values, that is all values of nth step, we are taking the neighboring cells, the upper cell, lower cell, left side, right side, or if you are talking in compass directions, that is north, south, west, and east, and from the previous step, such a method is known as Jacobi's method. So for Jacobi's method, to find out the current value of the variable, we will be using values of previous iteration, that is values of neighboring cells from the previous iteration. All the values is taken from previous iteration. So the question is involves its current value and the values of neighbors from the dash iteration, that is option A, previous iteration. So if you remember uh, T I comma j is equal to T I plus 1 comma j plus T I minus 1 comma j plus T I comma j plus 1 plus T I comma j minus 1 by 4. If we are taking, so to find out n plus 1th iteration, the value of Tij at n plus 1 step is taken from, if it is all taken from the previous step, then it is Jacobi. If some values, that is the already swept direction, in which direction we have already swept, that direction is taken from the current step. That is, if we are at ij, we have already swept from moved from I minus 1. So we have already calculated this I minus 1 j step in the current iteration. Also, this j minus 1 point value we have already found out. So these two values are known in the current iteration itself. So these two values, that is I minus 1 value and j minus 1 value, is being taken from the current step. Then this method is, so then this becomes Gauss-Seidel method. That's the difference between Gauss-Seidel and Jacobi. So in Jacobi, all the values of neighbors is taken from the previous iteration, while in Gauss-Seidel methods, it is a mixture of current and previous. So and the latest updated values, to be exact, if it is for conceptual clarity, we can say it as the we are using the last updated values, because this ti minus 1 comma j and ti comma j minus 1 values have been updated lastly, while the ti plus 1 comma j and ti comma j plus 1, these two values, the last updation is only existing in the previous steps. So we can say that in Gauss-Seidel methods we are using latest updated values. Hope it's clear. Our answer is option A, previous. Moving on to next question. Moving on to next question. Question is, the primary purpose of artificial compressibility method in CFD is to. So the question is on artificial compressibility method. The question is about its primary purpose. What is the need of an artificial compressibility method in CFD? Options are directly solve compressible flow problems. Option B, simplify the pressure velocity coupling in incompressible flows. Option C, increase the density of the fluid being simulated. Option D, improve the accuracy of turbulence models. You can try to answer the question. You can inbox your answers. Yes, you are right. Answer is option B. So the pressure velocity coupling in incompressible flows. If you are remembering this artificial compressibility, the term artificial compressibility method is introduced uh, to convert or use so our primary purpose is to use or use the compressible flow solvers for incompressible flows. That is, uh, when there is incompressible flows, the issue is that there is a decoupling of pressure and velocity. So to couple this thing, we will be introducing a fictitious compressibility term that will help the established compressible flow solvers. Uh, this With the introduction of this fictitious compressibility term, we can use the compressible flow solvers to solve the incompressible flows. So option B is our answer. Moving on to next question. The artificial compressibility method introduces a new variable. Already discussed in the previous question. We are introducing something. So the question is about that particular thing. The question is about the artificial compressibility method introduces a new variable, and what is this variable typically called? Options are: is it pseudo density? Option B, is it pseudo pressure? Option C, is it artificial viscosity? Option D, is it pseudo Mach number? You can try to answer the question. It's comparably simple question. Write in box your answers. No, it's not artificial viscosity that we are using. We will be adding some terms called some density term, some pseudo density term. Uh, it's it's called uh, say the equation is becomes dou by dou t of rho star plus del dot u is equal to 0. Normally, the continuity equation is del dot u is equal to 0 for the flows, but in artificial compressibility method, what we will introduce this term, this transient term in the equation and make it dou by dou t of rho star plus del dot u is equal to 0. So this term is something what we are adding new. Next question. The artificial compressibility method utilizes two-step iterative process. What does the step primarily solve for? Options are: option A, momentum equations; option B, continuity equation; option C, pressure field; option D, all of the above. Try to answer the question. You can inbox your answers. As we have already mm, told that we are uh, introducing a new term in continuity equation, that is dou by dou t of rho star plus del dot u is equal to 0. So the thing is, this is a transient term. This is a transient term. And what we have to do is we will be iterating this term in a pseudo time loop. So we have to uh, iterate this uh, we have to iterate this transient term in a pseudo time iteration loop and march it towards a steady state. Then only we can use it for what? Use it for converting the incompressible nature to a compressible solvers. So the thing is we will be having two-step iterative process. The pseudo time iteration step will be adding to the normal iterative steps. So this is being done in the continuity equation, option B. So option B is our answer. Moving on to next question. How does the artificial compressibility method achieve a convergence to an incompressible solution? So again, the question is on artificial compressibility method. So question is how we will be achieving convergence of an incompressible solution. Options are option A, by setting pseudo density to a constant value. Option B, by iteratively reducing the magnitude of pseudo compressibility term. Option C, by increasing the time step size in pseudo time iteration. Option D, by directly solving the continuity equation. So the question is about how we will be able to achieve a convergence in a incompressible flow problem using artificial compressibility method. Try to answer the question. You can inbox your answers. Yes, you're right. Option B is our answer. So in the previous step itself, I have told that we are introducing a new term, that is dou by dou of rho star. So this has to be this term is actually not there in the equation. We are introducing this. So in order to nullify the effect of the terms we have introduced, we have to reduce the magnitude. So we have to reduce the magnitude of this term by time marching it. So we have to run a time iteration loop in which it becomes that term's magnitude will reduces and becomes 0. So our answer is option B. Next question. The artificial compressibility method can be considered as a type of. So what is the general, uh, in which category does this artificial compressibility method best fit? The options are option A, is it a turbulence model? Option B, is it a preconditioning method? Option C, is it a discretization scheme? Option D, is it a boundary condition treatment? Try to answer the question. You can easily eliminate some of the options and reach into the answer. You can inbox your answers. No, it's not a turbulence model. It is actually a preconditioning method. So basically, what is turbulence model? When we have turbulence, there will be eddies. There will be disturbance or rotations or eddies and all. So when we are modeling these eddies, that is something what's called turbulence models. So the methods like LES, large eddy simulation, RNS, RANS, NAVE, Reynolds average, Navier-Stokes equations. All these are turbulence modeling terms, where we will be modeling the turbulence or eddies or of uh, according to our requirement. So such terms are called turbulence models. So artificial compressibility term is for incompressible flows. So we need when the flow is incompressible. It's it's about the incompressibility of the flow. The As you may know, the incompressibility is a flow property. What we are taking here, so it is for incompressible flows or turbulent flows. Don't uh, mix up with the two. Turbulence and incompressibility is different things. So it's mostly for incompressible, to model incompressibility or to method to solve incompressible flows using compressible flow solvers. So it's actually a preconditioning method. So we are adding the compressibilities, artificial compressibility term, the zero density term that we are introducing in the continuity equation. So it is a preconditioning. So before solving the momentum equation, we are introducing it itself in the continuity equation itself. So it's a preconditioning method. So and option C, option C is discretization schemes. We have seen central differencing scheme, upwind scheme, forward differencing, backward differencing. All such methods are called discretization schemes. And boundary condition treatment, again, we know a type of boundary conditions and boundary conditions, how it is being incorporated in the discretization scheme. All such things are different, but here artificial compressibility is a preconditioning method or preconditioning technique. Moving on to next question: what is the crucial aspect to consider when implementing the artificial compressibility method? So what is the important thing, uh, important aspect while considering or when we are implementing the artificial compressibility method? Options are: option A, selecting a high value for pseudo density; option B, choosing an appropriate time step size for, for the physical time step; option C, determining the optimal value of pseudo compressibility time; option D, defining a complex turbulence model. You can try to answer the question. You can inbox your answers. Yes, option C is the right answer. That is determining a pseudo compressibility time. And you can keep in mind that whenever there is most commonly when in CFD method, uh, uh, when we have such a question, always go for optimum, the options containing optimum, because when we are going for low values in most of the terms, general term, but it can vary. Suppose we have some particular quantities or parameters, when we are going for low values, it will result in inaccuracies or insufficiencies in the result, while when we are going for high values, it will lead to so for any parameter, for most of the parameters. But I'm not making it general, but there will be case to case difference. But uh, some, as a initial troubleshooting, we can take consider this. So when we have a CFD parameter, if we are going for some low values, it will result in inaccuracies in the result or insufficiencies in the method. Or when we are going for the high values, very high values, it will increase the computational complexity as well as memory usage. So this will, so what we have to choose is mostly the optimum value. So this will be true for most of the cases, but there are instances that we will look later where we have to go for high values or low values. That's a case to case basis, but as a rule of thumb, you can generally consider you such option you can uh, think later. The first you can try to check the other options when you have such a question. Moving on to next question. And the question is again on stream function vorticity method. Which equation is solved for in stream function vorticity method? So the question is that which is the equation that is used for stream function in the stream function vorticity method? Option A, the continuity equation, that is del dot u is equal to 0. Option B, Navier-Stokes equation or momentum conservation equations. Option C, Poisson equation for pressure. Option D, a biharmonic equation derived from vorticity and stream function relationships. We can try to answer the question. We have discussed this earlier also. You can inbox your answers. Uh, okay. Uh, our answer is option D, biharmonic equation derived from vorticity and stream function relationships. We have already told that we have stream function defined as uh, dou psi by dou y is equal to u and dou psi by dou x is equal to minus v. So this is relations between u and uv and psi. Also, we have our del cross v, that is the velocity vector itself, is equal to 0 for vorticity. So these two set of equations, uh, this is the called of velocity, and this is the definition of or relation of psi with respect to u and v. So these set of biharmonic relationships uh, is used to solve for this stream function psi. Our option is option B. Next question. Next question. Which numerical discretization techniques are commonly used with stream function vorticity method? Options are: option A, finite difference method on structured grids. Option B, finite element methods on unstructured grids. Option C, both finite difference and finite element methods. Option D, spectral methods for high accuracy solutions. So which is the numerical discretization method that we will be clubbing with stream function vorticity method? You can try to answer the question. You can inbox your answers. Yes, we can use it with both finite difference method and finite element method. Our answer is option C. Both finite difference method and finite elements method can be used for stream function vorticity method. Next question. The stream function vorticity method is particularly well suited for solving which type of flows? So uh, again, a question on stream function vorticity method. It is on the applicability or application of the method. Options are: option A, high speed compressible flows with shock waves. Option B, turbulent flows with vortex structures. Option C, steady or time dependent, that's steady or unsteady incompressible flow in two-dimensional flows. Option D, flows with strong pressure gradients and separation. We can try to answer the question. Yes, you are right. It's option C is the right answer. Yes, as we know, stream function vorticity method is a method like artificial incompressibility method. It is another method or formulation to use. Sorry, formulation for pressure velocity coupling or solving pressure velocity to overcome the pressure velocity uh, decoupling issues that is faced in incompressible flows. So it is mainly for our purpose or our need of stream function vorticity method is to solve for incompressible flows. So again, interestingly, there is additional term called two-dimensional flows. Uh, I can even say why is it restricted to two-dimensional, or can we use it on three dimensions also? If our flow is a 3D three-dimensional incompressible flow, can we use stream function vorticity method? You can inbox your answers. Yes, true, true. Again, we the only thing is there's this is a limitation of this method, stream function vorticity method. That is, we can only use this method for stream function in two-dimensional flows because there is no stream function or psi defined in three dimension. So psi only exists for 2D. Psi doesn't exist for that is stream function doesn't exist for three-dimensional flows. So our option is option C. Moving on to next question. The stream function vorticity formulation solves for which two fundamental variables in two-dimensional incompressible flows? Again, it's a simple question. From actually, I should have asked this question earlier. So now we know options are velocity components u and v. Option B pressure P and vorticity. Option D option C stream function and vorticity. Option D velocity magnitude and direction. So we know it is stream function and vorticity. Our answer is option C. So pardon this consider it as capital letter omega. The small omega mostly we use for angular velocities. For vorticity, the capital letter omega is mostly used. So we will be used for the formulation is psi omega. Moving on to next question. Which property of the stream function is crucial in stream function vorticity method? Options are option A, it represents the total mechanical energy of the flow. Option B, its gradient is perpendicular to the velocity vector. Option C, it directly relates to the pressure field. Option D, it defines the circulation around a closed curve. You can try to answer the question. You can inbox your answers. It's not about the mechanical energy of the flow. It's option B. Its gradient is perpendicular to the velocity vector. And also option C is also true, but uh, uh, if you see that we have already uh, discussed that dou psi by dou y is equal to u, and dou psi by dou x is equal to minus v. So from this formulation, the it's a gradient of these forms. The gradient of the stream functions will be yielding velocity components. So we can solve u and v indirectly by using psi. Moving on to next question. What is a significant advantage of stream function and vorticity method? The question is about on the advantage of stream function vorticity method. Options are option A, it directly solves for the pressure field, eliminating the need for pressure velocity coupling. Option B, it, it is computationally more efficient than solving for velocity components directly. Option C, it can easily handle complex boundary conditions. Option D, it is particularly used for turbulent flow simulations. You can try to answer the questions. You can inbox your answers. Okay, we can, if you remember previous question discussions, uh, we can easily eliminate some of the options. Like option C, it can easily handle complex boundary condition. We have seen that it has stream function vorticity method have a difficulty in handling almost all the boundary conditions. And option D, again we can eliminate because stream function vorticity method is not about turbulent flow modeling. Option B, and it says it is becomes computationally more efficient. That again we can eliminate because we are uh, solving for we are only indirectly solving for velocity components u and v. So we are finding psi first, then we are finding u and v. So it won't be computationally efficient. So only option left is option A. It solves for pressure field directly, eliminating the need for pressure velocity coupling. This again we have discussed before that the need for stream function vorticity method is due to the uh, difficulty of coupling pressure velocity coupling in incompressible flows. So option A is our answer. Next question. Artificial compressibility method is best suited for. So the question is about when to use artificial compressibility method. Option A, high Mach number flows with shock waves. Option B, low Mach number flows with incompressibility or low Mach number incompressible flows. Option C, turbulent boundary layer simulation. Option D, multi-phase flow problems with interfaces. Again, simple question. You can try to answer the question. Please inbox your answers. Yes, option B is our answer. Option B. Because from seeing this itself, we can say it is for incompressible flows. Next question. Which method is generally considered as less efficient than Gauss elimination and LU decomposition for large sparse system of equations? Options are option A Gauss elimination, option B Jacobi method, option C LU decomposition, option D all of the above. This is again a simple question. The only option left from the equation itself, from the question itself is Jacobi method. Option A, option B. Next question. In CFD applications, solving system of equation often involves discretizing the governing equations leading to dash matrices. Take it as dash. So leading to dash matrices. Option A, diagonal matrices. Option B, sparse matrices. Option C, full matrices. Option D, random matrices. You can try to answer the question. Box your answers. Yes, option B, sparse matrices. So we have already discussed what is sparse matrices, where the number of zeros will be more than the number of non-zero elements. So mostly when we are discretizing the governing equation, it will mostly lead to sparse matrices, from which we can convert into diagonal matrices and all, not diagonal, banded matrices. So our answer is option B, sparse. Next question. Which method is known for its simplicity and ease of implementation? Options are option A Gauss elimination, option B Jacobi method, option C LU decomposition, option D relaxation method. It's option B Jacobi method. Jacobi method, even though it's less efficient compared to Gauss-Seidel and all, from the list, it is not for the simplicity and implementation. Even though Gauss elimination method is it's a direct method, LUD combustion method is not that simple and straightforward. Uh, Relaxation method is another iterative method. So from the options, it's option B, Jacobi method. Next question. In LU decomposition, the forward substitution step involves for dash using the dash matrix. So we have two dashes. This is a fill in the blanks kind of problem. Uh, Here, the question is for in LU decomposition, in LU decomposition method, when did or when did the forward substitution takes place, and for what we will be using forward substitution. The answer pairs are option A, unknowns using the lower triangular matrix. Option B, unknowns for the upper triangular matrix. Option C, diagonal elements using the lower triangular matrix. Option D, diagonal elements for the upper triangular matrix. You can inbox your answers. Yes, the option is option A, unknowns for the unknowns using the lower triangular matrix. For in when our quotient matrix A is written as LU, where L is a lower triangle matrix and U is an upper triangle matrix, the forward substitution mostly happens in lower triangle matrix, and it happens for unknowns. So our answer is option A. Next question: which method is used as an iterative refinement technique after applying direct methods like LU decomposition? So the basic question is which is iterative uh, refinement technique from the options listed below. Options are option A, Gauss elimination, option B, Jacobi method, option C, relaxation method, option D, all the above. Uh, yes, Jacobi is an answer, but this is a tricky question. Actually, both B and C are answers. Like I already explained in the previous question, that relaxation method is also an iterative method. So both Jacobi method and relaxation method can be used as uh, iterative refinement techniques, whereas Gauss elimination is a kind of direct method. It's not an iterative process. Gauss seidel is a iterative process, iterative method, while Gauss elimination is not. So Jacobi and relaxation method both can be used as iterative refinement technique. But yes, you can say from it's, Jacobi is the straight answer. More accurate is Jacobi, but both relaxation can also be considered. Next question: the mathematical framework of the artificial compressibility method involves. The next question is on artificial compressibility. So the question is about. Give me 1 second. Okay, the question is on the mathematical framework or the basic idea of the artificial compressibility method involves. Mathematically, what is being happening? Uh, Options are direct modification of the continuity equation. Option B, introduction of a source term in the momentum equation. Option C, elimination of the pressure term from the governing equations. Option D, transformation of incompressible system into a hyperbolic system. You can inbox your answers. Uh, no, it's not option A. Okay, it's kind of a trap. Uh, uh, yes, we are actually converting the continuity equation, the dou t by dou t of rho star plus continuity equation is equal to del dot u is equal to 0. So, what initially the continuity equation is del dot u is 0 for incompressible flows, which will be modified to this one. But the question is about mathematical framework. Mathematically, what is being happening? So what we are doing is we are converting the system of equation, that is incompressible system, into a hyperbolic system, that is dou by dou t. This term is introduced here. So such kind of equations, if you have remember our discussion on type of PDEs. So it is what essentially it is being doing. It is converting this system into a hyperbolic system. So option D is our answer. Is something what uh, just option which will be suiting more to the question. Moving on to next question. Compared to pressure-based solvers for incompressible flows, the artificial compressibility method options are always achieves faster convergence. Option B may require additional computational resources. Option C inherently less accurate. Option D cannot handle unsteady flow simulations. So the question is about a comparison between pressure-based solvers and artificial compressibility method. You can inbox your answers. No, it's not option C. It's option B. It may require additional computational resources. So the modified equation is dou by dou t. I am repeatedly writing this. Dou by dou t of rho star plus del dot u is equal to 0. So this is a fictitious thing or added thing to the system which is not there. So it's an additional thing, and this additional term, this fictitious term to be is to be time marched using a pseudo sorry of time loop, time iteration loop. So this time should be a time march towards steady state using a time iteration loop, and that will that so we are adding two different loops. So once this time should be time march towards stable, that when this when it becomes steady, this time becomes zero. So we have to time march it to a steady state. Then the other loop, the outer loop or the other loop will be running. So we have to run two loops of iterations. So which will in essentially what will do is it will uh, add up to the computational cost. So our answer is option B. So we can wind up for today's session. Thank you for joining.